To draw organic structures quickly, you do not necessarily need to draw out each atom and its available electrons and mix and match them, because that can get downright tedious. What you do need to know is the periodic table and where elements fall in it. What's useful to do is take the simplified periodic table and number it. 1, 2, 3, 4. Once you get to 4, start counting backwards. 3, 2, 1, 0. What these numbers represent are the number of bonds in order for a molecule, for an atom, to be neutrally charged. Hydrogen, lithium, sodium, 1 bond. Magnesium, calcium, 2. Boron, aluminum, 3. Carbon, 4. Nitrogen, 3. Oxygen, 2. Fluorine, 1. Now, what's useful about this is that when you form 4 bonds, that means you form a tetravalent system or quad, 4 bonds. 3 is a trivalent. 2 is a divalent, or 2 bonds. 1 is a monovalent, 1. So hydrogen is an M, and fluorine, chlorine, bromine, and iodine are M's. When you have this idea in mind of what constitutes a Q, a T, and M, you can use this double bond equivalent equation to figure out how many pi bonds or rings are in a system even before you begin. So we do that by using this equation, 2Q plus 2 minus M plus T all over 2. Take this formula here, C4H10. Well, when we plug in the numbers for the double bond equation, 2 times, well, Q is carbon, 4. So 2 times 4 plus 2 minus M. In this case, we have 10 hydrogens. Those are the M's for the monovalent. We divide that all by 2. 2 times 4 is 8. 8 plus 2 is 10. 10 minus 10 is 0. So this particular formula, C4H10, has a DBE of 0. That means there are no double bond equivalents to this. Now, with that said, we can start by drawing this molecule out. Start by drawing the carbons out. I usually go 1 carbon less than what is there. So here we have 4 carbons, so I'm going to draw 3 carbons, like that. Now we have a 4th carbon to add on. We can add it to this end carbon or the middle one. If we add it to the middle one, we get this. If we add it to the end one, we get this. And we get 2 possible structures. Now, we don't have any double bond equivalents, so we don't add any pi bonds or anything like that. So these 2 structures match the formula C4H10. And we can even count it. This has 4 carbons, and then this is CH3, so we have 3 hydrogens, 3 hydrogens, 3 hydrogens, that's 9 hydrogens, plus the 1 hydrogen in the middle, that's 10. Or here, we have the 4 carbons, and then we have 3 hydrogens here, 2 hydrogens there, that's 5, plus 2 hydrogens here, that's 7, plus 3 hydrogens here, that's 10. So C4H10. These 2 match that. Let's take a look at C6H10O. Again, we plug in the numbers for the double bond equivalents formula. 2 times Q, so 2 times the number of carbons, 2 times 6, plus 2, minus the number of hydrogens. Now oxygen is a D, it's a divalent. Notice there are no D's in the DBE equation. That's because oxygen doesn't count. You can have 20 oxygens, 30 oxygens, it doesn't matter to the equation at all. We divide this by 2. 2 times 6 is 12. 12 plus 2 is 14. 14 minus 10 is 4. So 4 divided by 2 is 2. So we get 2 DBEs. And so what we can do is draw this molecule out. I'm going to draw out all 6 carbons like so. 1, 2, 3, 4, 5, 6. And then at the end, I'm going to draw in the oxygen. Then we need to draw in any hydrogens attached to non-carbon atoms. So like here. And we'll add in the double bond equivalents. So if we add in a double bond equivalence, we need 2 of them. We can add in 1 here, 1 here. This matches the formula. 1, so we have 2 hydrogens plus 1 here, that's 3 hydrogens, plus 1 there, 4, 5, 6, 7, 8, 9, 10. So this matches the formula C6H10O. Could have also changed the double bond equivalence, so we could have the double bond equivalent here, and maybe 1 here. This also matches the formula. We could have put the oxygen attached to maybe the center one. And then we could have had the double bond equivalent here or here. Other things we could have done is maybe use our 6 carbon atoms as a ring. In this case, this takes up 1 DBE, double bond equivalent, because it forms a ring. We add in our oxygen, and then we can put the other double bond equivalent in. So this also has the formula. There are lots of different structures that have this particular formula in it. Let's take a look at C5H9N. Do the DBE formula. 2 times 5 plus 2 minus 9. Now, nitrogen is a T. So we add in the number of T's, number of nitrogens. That's 1. Divide that all by 2. 2 times 5 is 10. 10 plus 2 is 12. 12 minus 9 is 3. 3 plus 1 is 4. So 4 divided by 2. We get, again, 2 double bond equivalents. And so we can draw in 5 carbons, and then we can add a nitrogen in, like so. Now we need to add in 2 double bond equivalents. Well, a carbon-carbon triple bond, or carbon-nitrogen triple bond, will count as 2 double bond equivalents, so we can add it in like so. When we do so on a carbon-carbon triple bond, we have to be a little bit careful. This is actually incorrect because we have formed, notice right here, it has to do with this bond angle. Bad way of drawing this. When we add in a triple bond, we should redraw the structure. So the bond angle is 180 degrees, like so. This good, this is good. So we have the 3 hydrogens here, plus the 2 hydrogens there, that's 5, plus 2, that's 7. 7 plus 2 more is 9. We have the 1 nitrogen, and 1, 2, 3, 4, 5, and the 5 hydrogens, 5 carbons. So this is correct. There are lots more possibilities.